Programming microcontrollers at the register level can be a long-winded and tedious process. So each peripheral tends to have several registers that control it, and each register is 32 bits wide. So you need to go through the datasheet or the user manual to read the data about all the different registers and figure out which values, which bit in the registers need to be set or cleared. So the LPC 1768 user manual is nearly 850 pages long. So imagine going through that user manual, trying to find all the registers in there, reading the description, figuring out whether each bit in each register needs to be a 1 or a 0. So it can take a while, very easy to make mistakes. But fortunately, the Mbed platform has been developed, which provides a high-level application programming interface, or API, library. This essentially is a collection of C++ classes that abstract away this low-level bit values of the registers. And this means it's much quicker to develop embedded software. I often see it called rapid prototyping. So rather than having to dig through this 850-page manual, you can get up, just a few lines of code, very easy to use classes. You can start developing applications. So if you want to create a digital output, so an output on a GPIO pin, we do that using the digital out class. So we create a digital out object. So this is created using the constructor, and we pass in the value of the pin that we want to use. So we can use any of the I think it's P5 to P30. So in this part here, you could put P5 up to P30 in there. But you can also use the LEDs that are on board, because the Mbed board itself has got 4 LEDs on board, so they're called LED 1 to LED 4. So we can create, you basically create a digital out object, connect it to a particular pin, and then we can just use that object in our code to control the pin. So you can see in this example here, we need to use, to do this, we need to include the Mbed, library. And then here we're creating our object. So here, this is our class. So the class name is digital out. I've created an object called LED, and I said, right, that LED correspond, this object corresponds, is going to essentially control LED 4. So this is one of the onboard LEDs. And then in our main function, we've just got a while one loop. So this is, this code is just going to run repeatedly. It's just in this infinite loop. And then you can see I've used a write method. So this is by writing a value to that pin, we can essentially control the voltage on that pin and hence control the LED. So we do that using this dot syntax. So you can see I've got LED dot write, and then in brackets I've put 0, so you can guess that's going to put a comment here, that's going to put 0 volts on the pin. So that's going to cause LED, because these LEDs actually are positive logic, so that will turn the LED off. Then another function what's part of this Mbed API is a wait one. So we can use this wait function. So wait, and in brackets 0.5, we'll tell it to wait 0.5 seconds. So the LED will switch off. We'll wait for 0.5 seconds, and then we'll do LED.write 1. So that's going to put essentially 3.3 volts on that pin, cause the LED to come on. Then we'll wait 0.5 seconds again, and then go back. So you can, if you kind of plotted the voltage on the pin over time, we'd have 0 volts for 0.5 seconds. And then we'll get 3.3 volts. So this code will essentially cause this voltage waveform to appear on that pin, and so the LED will just blink. So we saw there the wait function. We use that to implement delays, and we can pass in the argument here is a floating point number. So this is this is either a floating point number or decimal number. But you can also use, there's also some other functions. There's the wait ms for wait milliseconds and wait us for wait microseconds. But for these functions, it's very important that you use integers. The arguments for these functions are not floating points. So if you did LED dot write milliseconds, you have to do, say, 5. You can't do 0.5 milliseconds. You have to be integer number of milliseconds and microseconds. So you can see on the front of the Mbed board, there's these LEDs, and they're labelled left to right, LED 1, LED 2, LED 3, LED 4. So in this case, when we run that code, this LED will blink on and off, LED 4. So in the previous examples we saw we could use a write method. So write is just a method inside of the digital out class. So you can use that to turn the pins on and off, but there's also this assignment operator what acts as a shortcut. So in this, when you do this, this essentially makes this object behave like a variable. You can use, if you assign 0 to that object, it'll turn the LED off, and if you assign 1 to it, it'll turn it on. So this is a shortcut, but I actually prefer the dot write method. I think it makes it clearer that LED then is an object and not a variable, because you might have in your code, for example, you might have int a, and then you've also got this LED. So if you do a equals 1, so LED equals 1, obviously them lines of code look very similar. It's not clear if a is a variable, is a is an object, if LED is a variable or it's an object. So actually doing LED dot write, I think just makes it clearer. It's a few more letters to type in. I think it just makes your code more clear, and it shows that you're dealing with an object rather than a variable. But you can use, both are acceptable. So I suggest you pick one and stick to it rather than keep changing, throughout your code. I think it's better to just pick one method and stick to it and just be consistent. So we saw then with the digital out class, we can control a single output pin, but it's actually possible to address multiple pins in one go by using this, what they call a bus out class. So again, this is a class here. So here I've made an object called LEDs, and in this constructor we actually specify all the pins we want to use, want to create that bus. So you can do, for the bus, you can have 2, 3, 4, 5, 6, up to how many you want really. But in this example, it's going to create a 4-bit bus. So you can see each of the LEDs is going to be a part of this bus. And it's worth noting the first one you put in the constructor is the least significant bit. So obviously this one's going to be the most significant bit. So there's a very good reason I've done it 4, 3, 2, 1, and that's so it matches up with the ordering on the actual development board. So now we've got this LEDs bus. It means we can write other values. We don't just have to write a 0 to 1. For this case, with 4 bits, we know we can go 0 up to 15. So now we've got our main function inside here. We've got our while loop, and then inside the while loop, I've got a for loop. So this for loop is just going to loop through these values here. So 0. In fact, that should be because we want to go 0. We basically want to count 0, 1, 2, 3, 4 up to 15. So you can see there's a bit of a typo here. That should be less than or equal to. So value equals 0, and we're going to keep looping up to value is 15. Now we can specify in hex here 0x 0f, and then val plus plus. I'll just make increments at the end of every loop. So the first time around this loop, LEDs will be equal to 0. Then we'll wait 0.25 seconds. Val will get incremented. So the next time in the for loop, LEDs will be equal to 1. Again, wait again, increment, LEDs will be 2, 3, 4, and that'll just keep repeating until we get to 15. And after that, we're at the end of the loop, so we'll break out of this for loop, we'll essentially go back to the beginning, and it'll start back at 0 again. So this bus is just going to count through 0, 1, 2, 3, 15, 0, 1, 2, 3, 4, 5, 15, and so on. So now, I've used this assignment kind of shortcut here, assign that value to the LED bus. So you can see when you have to look at the LEDs on front of the Mbed, for example. So when LEDs is just equal to 1, we're going to have a sense of 0, 0, 0, 1. So this LED will come on. And obviously for the case when it's 3, of 0, 0, 1, 1, and 0, 1, 1, 1, it'll obviously be 7. And then for the maximum value, 15 or 0x, 0f, there'll be 1 on each LED, and all the LEDs will light up. So that's using the bus out. And then finally we've got the digital in. So these are when we're using the digital inputs. So now, again, we've got our, for this example, I've kept the bus example in, but now I've created so this is our digital in class. I've created an object called button connected to pin 15, so we can use any of the P5 up to P30 pins. So now we can use this read method. So that returns a 0 or 1 depending on whether it's 0 or 3.3 volts on the input pin. So assume we've got it connected up as we've done before, as we've seen before, sorry. So when we come to this code, we enter the main function, then we come into this while loop, and then we're going to check. So if button.read is equivalent to 1, so be very careful here, we've used a double assignment, so this is a equality operator. So if button.read essentially returns a 1, this expression here will be true, and so we'll basically switch on all the LEDs. But if it's not true, we'll switch off all the LEDs. So this, depending if you're pressing the button or not pressing it, it's going to depend on how you've connected up the button. So if you use the pull-up resistor or pull-down resistor, it'll depend. It'll affect which one of these corresponds to the button being pressed or not pressed. So that was using this read method, but again, as a shortcut, we can use this this kind of assignment shortcut, because these objects essentially act as an int. So you can do, you just say if button, I've called it button here, if button is equivalent to 1, then switch all the LEDs on, else switch them off. So again, you can either use read or this, just kind of treating it like an integer. Both are equivalent. Just pick the method you like and stick to it. Now we'll just look at the mode. Because in the previous example, I was assuming that we had some kind of external pull-up resistor connected, but you might not want to bother using an external resistor, because there is internal ones inside. So we can use the mode method. So here again, there's the same example. We've got our button object connected to pin 15, but before we enter that loop, I'm going to set it, set the mode. So we've got button.mode, and then inside these brackets, we're passing our argument. So here I've put pull down, so that's going to switch on the pull down. But all the possible arguments are pull up or pull none, so it's not going to turn any on. So in this case, we won't need an external resistor, because we've turned on the internal pull down resistors. So essentially we've kind of we've got this. So inside we've turned on, essentially kind of turned on this internal a pull down resistor, and so oops, that's a 3.3 volts here. That's a switch. So you can see now when the button is not pressed, it's going to be a 0 on here. So if you don't press the button, essentially this will happen. That's not going to be true. So this expression will only be true when the button is pressed. So in this, because you often use pull down resistors as a kind of most logic, if you will, because then when you don't press the button, it's a 0, and when you do press the button, it's a 1. So by using this button, you can turn the button on, and the LEDs, press the button, and all the LEDs will switch on. We don't press the button, and all the LEDs will switch off.